section of material, basically, from here to the end. We've got chemistry to do from here to the end, and that's what we've got. So we've got this stuff, which is atoms in the periodic table, which I think you guys already had a dose of in like 6th, 7th, or 8th grade, depending on maybe which school you were at or how they did it. So we've got that to do. We've got chemical bonds, which will come after that, and then we've got balancing chemical equations will be our last bit. So that's what we've got left to finish off the year, like 3 tests to go plus final, and that's that. That's all we've got left to go. So this one is on atoms in the periodic table, is what we'll start with. And the question was, on page 36 in your interactive notebook, give me 3 things you know, 3 things like maybe you used to know that you don't know, so things you would like to know, and then 1 question that you still got left about atoms based on what you know already. So what I'd like to do is get a list up here on the board of the things we know. And this will help me figure out where I need to pick up with you guys, because I know that you've done this before. And some of you guys are probably fairly advanced, like in terms of what you know about atoms. So I need to know where I've got to start teaching with this stuff. So if you wouldn't mind, let's get a list. Lindsay?
Everything has atoms.
Okay, yeah, that's a good one. Is that true? Does air have atoms? Air's got atoms. Yeah, Lindsay, I was trying to see if you understood what she said. Everything that is matter is made up of atoms. So what's bigger, a cell or an atom? Cell's bigger, yeah. So number 1, if you didn't know this, atom, how did you say it, Lindsay? Everything is atoms. I'll shorten it like that. So that's true. Everything that's out there is made up of atoms. Do you know where there's a whole list of atoms? Yeah, right there. Everything you see on Earth, everything you see in space, everything you touch or feel, even things you can't see like air, are only made of that stuff. That's the only stuff that's out there. It's kind of like a cookbook, you know, when you want to make chocolate chip cookies or something like that. There's ingredients you need to mix together to make them. Those are the ingredients that make everything that exists that we know. Nathan?
Okay, so if everything is made of atoms, and so the air is made out of atoms, why isn't it like a wall? Why aren't we just trapped?
Because it's a gas. You're thinking of solids, right?
I guess so.
Yeah, solids, liquids, and gases.
But if the actual atoms themselves are technically solid, then...
Gotcha. All right, go ahead.
Atoms are or are one of the smallest things in existence.
All right, so I'll just write that they're small. Which is true. They're super small. Can you see them with a microscope? Nope, can't even see them with a microscope. You need something even smaller than a microscope. I don't even know, and I should know this, I don't know if we've ever seen an atom. I know that we can break them apart. We've got this, it's called CERN. I forget what it stands for, but in Europe they've got I think it's a 12-mile loop that they use to speed up atoms, and then they crash them together and kind of take a picture of what was there. Which, the first time they did it, some of the world's leading scientists were concerned, like, hey, please don't do that. It's going to cause a black hole. It's going to suck the world in. And the people that did it were like, we think we'll be all right. So they just did it anyway. It turns out it didn't make a black hole, and we're all still here, but could have, and that would have been the end of us. So anyway, everything's made up of atoms. Atoms are super small. What else, Skylar?
They're like protons, neutrons, and electrons.
So they're made of protons, neutrons, and electrons? Very good. So I'm going to write nu, and electrons. So they're made up of protons, neutrons, and electrons. That's a good one to have. What else about atoms? Remember, perhaps, for Madison, what the center of an atom is called? Yeah, very good. So, it's true for both. Middle. Nucleus. Nucleus. And there's two of these 3 things hang out in the nucleus. Do you you know the names of the things, Aubrey, that hang out in the nucleus? Very good. So I'm going to write P and N are in. And do you remember what the place is that the electrons spend their time in? It's called? There's two different words for it. One word is called the electron cloud, or energy level are the two words for it. So protons and neutrons are in the center, and then electrons are in the outside. They're in the energy level, or in the cloud, or the energy level that's out there. What else for stuff that you know about electrons or atoms? Randall?
There's a lot of empty space between the electrons and
Yeah, that's good. So I'm going to stop numbering them here, but lots of empty. Do you know about atoms and movement? You know anything about that? Like atoms moving around? Skylar?
But when they get hotter, they well, okay. When they're colder, they're more closer together. They don't move as much.
True.
When they're hotter, they move around more and they vibrate kind of.
Yeah, very good. Yeah, think of yourself at like a 1 degree concert or something like that, where before the band starts playing, everyone's kind of huddled around. You know, everybody's squished in to get a look at Harry Potter or whatever up in the front. And then once they start playing their quote-unquote music, the people in the audience start to move around. So consider that like atoms and heat being applied to it. As the heat's applied to it, they start to move around, and there gets more space in between them. They move around further and further. So it's true, yeah. As stuff cools down, atoms move less and less and get closer together, and that's what creates a solid. And as they get hotter and hotter, they spread out, and that's what turns it from a solid to a liquid, and then a liquid to a gas, and so on. Did I have that right, Des? Is it Harry Potter in 1 degree? No. I'll get it one of these days. Anything else about atoms and stuff like that? All right. What about this? Weird to think that the atoms in you have been in other things. For instance, where do you get the atoms to make yourself bigger as you grow? Where does it come from? It's got to come from somewhere. How do you? Yeah, the food you eat. The food you eat stacks on and makes you grow taller or bigger. The water you drink helps you do the same thing. So let's think back. Those atoms that you take in through food, they come from like lettuce or a cow or whatever, right? And those things, what was the lettuce before it was lettuce? Close. Parts of it were dirt, right? It took up vitamins and nutrients from the soil. What else was part of it? Water, carbon dioxide from the air. And then what do they spread again on crops to help them grow? Yeah, and what is fertilizer?
Dung.
What's dung?
Animal excrement.
Yes. So the atoms that, when you're eating your nice lettuce sandwich, those atoms that are in the lettuce are only one step removed from being dung, to put it in Nathan's terms. So you're eating like poop, but you're one step away from poop. Okay, so that only means you're 2 steps away. Cows eat vegetables, right? Grasses, things like that, which use poop to grow, so the cow eats things, so you still get the turd. You're just getting it one step further away from where it started, which is kind of gross. And you're thinking, oh, or maybe you're thinking like, oh, that's so disgusting. Well, you can look at some cool stuff about it, because those atoms that are in the poo now or in the lettuce now or whatever have been around for billions of years. They could have been once dinosaurs, the atoms that are inside of you. They could have been somebody else, like previous, way back when. You could have atoms inside of you that were part of Julius Caesar, or atoms inside of you that were part of Cleopatra or something like that. Those things are around. The other thing to think about is that nice bottle of water that you have. Since all matter here on Earth gets recycled. When you drink your nice, cold, fresh water out of the bottle, like Evian or whatever it's called, Levian, I don't know. What is it? Faucet water for me, Fiji, whatever. You drink your nice water and you're like, oh, this is such fresh, clean water. I'm glad I'm drinking such fresh, clean water. That's great, right? But when you do a number one and you flush it, where does it go? It goes to the sewage plant, right? Does its thing. And then from the sewage plant, where does it go? Into the rivers, down into the ocean, where it evaporates and then rains back down upon you where you drink it. So, the pee that you got rid of, or that some other person you've never met got rid of last year or last week or 50 years ago, that has been like processed and in a river and then it rains back and you're just drinking it again. So the water you're drinking has already been drank before, and probably multiple times before. So remember that as you're paying $2 or $3 for your bottle of recycled and processed urine, that looks nice and clean now. Because it is nice and clean. There's no way around it. You need it. But it's already been used. Hate to tell you. So, on that note, I'm thirsty. Yeah, Nathan?
So what you're saying is that every drink of water...
Those atoms that are on the periodic table right there, and they've all been recycled. They've all been used, and they will all be used again. When you're used up and gone, somebody will use up your atoms, the stuff that you're using right now. Even in terms of like how you breathe. The stuff you breathe out, other people will breathe in. Somebody famous, when you went to a concert for like your One Direction or your One Degree concert or your Justin Bieber concert or whatever, you go there and he's breathing out, you're breathing in the same air that he is. Oh my gosh. It's like...
Is that right to blend with like 110, 111, 112? There's 113, 114, but those don't even have that.
We'll save that for the question time. It's one of my favorite ones to do, believe it or not. All these ones are. It's all like fun and like logical to me. So hopefully you guys find it the same way. One of the things you're going to be asked to do, and that's why I gave you the periodic table now, is to memorize atoms from 1 to 18. So that's going to be name, number, and symbol, from hydrogen all the way to argon. And there's a couple ways to do it. The one way is, just do one a day with a flashcard or something like that until you get there. And the test for these will be when we take our test on the unit. The other way, and the way that'll stick with you probably most easily, is if you go to your YouTube machine and type in periodic table elements in order song. The song just sticks in your head. It's childish. It's going to annoy you because you won't be able to get it out of your head, but you're guaranteed to remember the elements. 2 to 3 weeks out. So, and if you're thinking like, oh, that's so not cool to have the element song, that's like lame. But the dude from Harry Potter, the Harry Potter actor, Harry Styles or whatever it was, he was on one of the late night shows and he recited all the periodic table of the elements things. So just in case you don't think it's cool, Harry Styles knows them all in order. That's the host. It's either him or Jimmy Fallon, one of the two. Probably Jimmy Kimmel. But yeah, Harry Styles, he knows them all. And Harry Styles can rap. Who would have thought Harry Potter can rap? It's true. You can look it up. So, what we are going to do today, we've got 2 things basically to do today. Number 1, you guys grabbed this when you came in. This reading, it says on the front, atomic structure right here. So what I'm going to have you do in your table group today is you guys are going to go through, and this is on page 36 as well. So on that page 36, and if you need room, you're going to tape a piece of paper in there. You guys will read through this short article on atomic structure, and you and your group are going to highlight and write down on that Cornell Notes paper the things that you find to be most important. So we're going to go through, and we want all the information that's important out of there. When you're done with that, I'm going to go over with you how to incorporate that information into what we're going to do today, which is called a Bohr diagram. So those are the 2 pieces today. And as you get your Cornell Notes set up for this, your essential questions right here. And it says, how do atomic components influence the atom? So how do the parts of the atom influence the atom? So again, in your table group, you want to be on page 36. You can highlight, you can write, you can do whatever on that piece of paper. But the information from there needs to go into your notes on the Cornell notes. 36. Go over some of the points up here that I found to be most important and things I need to make sure you've got down so that as we make our way through this, we're all kind of on level ground as we start. So one of the first things I'd like to go over are a couple of terms that they bring up in that article. One being atomic number. That's the first one. And I was curious if anybody got a definition for that down in the notes that they took on there. Randall? Very good. It's the number. And if you don't have this down, you certainly want it down. That's one you've got to have. Number of. Can I use a symbol for proton so I don't have to write proton out every time? If I go P plus, does that work for you guys? So the number of protons in an atom. If you look at a box on your periodic table, the atomic number is the one that's like top dead center right there. That's the atomic number. And it's the same way on every periodic table that I know of. And so if you can find any element on there, you can tell how many protons it has. For instance, if you guys have your periodic table handy, can you find sodium on there? Its symbol is Na, and it's on the left-hand side. Everybody found sodium? And if I asked you how many protons it has, you'd be able to tell me 11. It's the atomic number. So the number on top of it tells you the atomic number. Everybody knows gold, but they don't know the symbol for gold. It's AU. Some people know the symbol for gold. You guys find AU on there? It should be number 79 or so, bottom center. Okay. How many protons? 79. How do you know? It's the atomic number. So that number in the box tells you how many protons are there. The next one I want to bring up relates to this, and it is that it mentioned in there something about atoms being neutral. I think it was in the first paragraph. Did anybody get down that little note that it mentioned about atoms being neutral? No problem. So one thing you absolutely want to have down in there is that all atoms are neutral unless noted. So if they're not neutral, there will be a sign next to them that we'll talk about later on that will tell you they're not neutral. But this says that all atoms are neutral, and that's important. It's important because it helps you figure out the number of electrons as long as you know the charges. If you look at protons, which are here, I gave away the charge already. What charge does a proton have? Positive. Electrons, did you get that charge? Negative, very good. And then finally, neutrons have neutral, yeah. So the way I remember that is protons. Pro is like a positive if you're doing pro and con. Electron, I think of electricity, and to me it hurts, so it's a negative. If you've ever been electrocuted, you would recognize that it's not comfortable, so I think of that as a negative. And then neutron sounds like neutral. That's how I keep those straight. So this is a key, because it says that atoms are neutral, which would mean that they're not positive or negative. It means that the positives and the negatives cancel out. So, for example, if we go back to the first one we looked at, sodium, and it says it has 11 protons, right? If that's true and it's neutral, or protons are positive, how many electrons would it have? Same number, because protons and electrons are going to cancel out. For every positive, there's going to be a negative. If you find gold again and look on there, how many electrons would gold have? 79. Yeah, very good. Same number, right? In fact, we could do it for either one. Can you guys find calcium on there, which is just down 1 and over 1 from sodium? How many protons, Gabe? How many electrons? Very good. So it's as simple as that. That's what those numbers mean on the periodic table. Those numbers on top tell you proton and electron for everything on the periodic table. There's one component, though, we haven't talked about, and that's neutron. Did anybody get down how to figure out the number of neutrons from those notes that you took? All right. So far we know protons and neutrons are equal to the atomic number, or protons and electrons, sorry. Neutrons are equal to this. At the very bottom, I've got to have a different note here first. So the next thing we need to write down is atomic mass is the next thing we got to have written down. And I know that was a vocab word in there, so he's got the definition. Junior, you got the definition for atomic mass on there? Negative. Randall? All right. So atomic mass is equal to protons, which is P plus neutrons, which is NO. So the mass number is equal to the protons plus the neutrons. And if you look on your periodic table, right at the bottom there, you're going to see a number with some decimal points after it. Like, for example, on sodium, isn't it like 22 point something? 22.9. So it's a 0.9 on there because there's different isotopes of it, which we'll also talk about later. But for our purposes, all you have to do to get atomic mass is round that number off. So 22.9 is going to round to 23. So we're just going to call that a whole number. So atomic mass, we're going to use a whole number to represent it. Can you find gold on there again? Number 79. When you get its atomic mass, what is it? Ethan, can you find gold on there? What's its atomic mass? Except that we're going to use a whole number, so it's 197, right? So last bit, to figure out the number of neutrons is this. Since we know protons plus neutrons equals our mass number, if we know what our mass number is, we can just take away protons and we get neutrons. So to get neutrons, which is N sub O, or NO, equals mass minus protons. Because mass is protons plus neutrons. If we want to figure out what neutrons are, we take away protons from mass, and what's left behind is the neutrons. So far, so good? All right. Here comes what's going to go on your page number 35, the page that's next to it, the output. To do this, you're going to have to use your periodic table. On there, we're going to do the 18 elements that we've got here. And what we're going to do is, you're not going to make a box yet because you want to see how big you're going to draw and you want to leave enough room for 18 of them. You're going to put a circle, and that's going to represent the nucleus of an atom. So you want to be on like the top left part of that page. If you could put a circle in there and leave yourself some room around that circle, that would be perfect. 35. So you want a circle, leave a little room around it. Inside that circle, or not inside that circle, above and to the right of that circle, we're going to put the element we're talking about. And the first one we're going to talk about, its symbol is H, and that is hydrogen. So we want an H above and to the right of it. Above and to the left of it, we want the number of protons that it has. So if you look, its atomic number. So for hydrogen, what's hydrogen's atomic number here, Lindsay? Top left corner, sorry. Yep. So up here, you want the number 1. Next to it, you want the letter H. Inside of your circle, you're going to tell me how many protons and neutrons are there by doing this. If you look at hydrogen, its atomic number is 1. So how many protons does it have? 1. So you're going to put a 1 B plus, because it's got 1 proton. And then remember, protons plus neutrons equal its atomic mass. If you look on your chart, what's the atomic mass when you round it off of hydrogen? 1. 1 plus what gets you 1? 0. So how many neutrons does it have?
0.0797.
Nope, 0 neutrons. We round that off, remember. So 0 neutrons, so you don't need to write anything for neutrons there. And then the last bit is the electrons. And here's how you do the electrons. Can you see how hydrogen is in like the first row, and that under that lithium's in the second row, and under that sodium's in the third row? Whatever row it's in, that tells you how many circles to draw around your nucleus. So since hydrogen's in the first row, it gets 1 circle around it. And remember, all atoms are neutral. So how many electrons, or hydrogen, because all atoms are neutral and it's got 1 proton, that would mean it's going to have 1 electron, and an electron is represented like that, as 1 slash in that ring right there. When you've got your size down, or you can put a box around it, and that'll be our hydrogen. That's a Bohr diagram, the symbol, the number like that. So we can move on and do helium right after that. Are you guys okay to move to helium? Okay. We'll do helium, and then we'll go down and do lithium and call it good. So, start with the circle again. And inside that circle is where we're going to put the number of protons and neutrons. So if we're looking at helium, its atomic number is 2. So how many protons does it have? 2. So it's got 2 P pluses. And then how do we figure out mass? Do you remember how we figure out mass, Gwen? Very good. So for our purposes, we're going to round off that number up there. So 4.0026 rounds to 4. So 2 plus something has to get you 4. 2. That would mean it's got 2 neutrons like that. Looking good so far. Up here we want its atomic number, which was 2. And then, how many circles get drawn around it? 1 circle. And how many electrons in that 1 circle? 2 electrons. As you read through there, did you notice that there are a certain number of electrons that can go in each layer? Remember how many go in the first layer? 2. And then every layer after that gets 8. So there's our 2 in the first layer. And that's one of the ways the periodic table is set up. See how there's only 2 elements in that first row? That's because they only hold 2 electrons. If we go down to the next one, how many elements are in that row? 8.
Yeah.
That's because they can hold 8. So we'll take a look at the next one, and then I'll let you guys go here. So the next one is lithium. And that's a 3 and an Li. Your circle, how many protons in lithium? 3 protons. And then when you round lithium off, it rounds to 7. So 3 plus something gets you 7. That'd be 4 neutrons. It's in the second row down. So how many circles? 2 circles around it. 1, 2. And how many total electrons? Same as its atomic number. 3. Do you remember how many can fit in the very first run? 2. So 2 of them go here. They show up as pairs. And then we've only got 1 electron left to place, so it's got to go in the row outside that, or in the level outside that. So your homework is to make it through argon, through 18. And the same thing. You should have noticed a couple things, that every time the protons increase by 1, every time the electrons increase by 1, but neutrons don't increase by the same amount each time. Neutrons change as it changes. So neutrons you can't do that with. So your homework is to just finish those off.